Good afternoon, everyone, and welcome to CON310, Running Batch Processes on ECS. My name is Asha Chakrabarty, and I'm a Solutions Architect with AWS. And joining me today to present will be Will White, who's an engineering lead from Mapbox. So what are we going to talk about today? We're going to talk a little bit about some of the characteristics and challenges of running batch processes, understanding how why Amazon ECS is compelling for running your batch workload. We'll walk through some recommended design patterns as well as best practices. And Will's going to come up on stage and talk about how Mapbox is using ECS to run their batch architectures. So what are some of the challenges of running batch workloads today? So typically, batch workloads tend to be very resource intensive and place heavy demands on both your system and application architectures. They also typically need to be completed within a certain period of time. And if you're using the same infrastructure to run multiple batch jobs, one batch job could adversely affect the other if it needs more resources, causing bad performance for the other job. You have to be able to scale your infrastructure resources for your batch workload that would probably keep it increasing in size due to the increase in data size as well. And you want to be able to, your entire infrastructure that's running your batch architecture, you want to be able to utilize each machine to its full capacity and at the same time make it cost effective. So what is it that batch workloads actually need? Firstly, reliability. If a job fails, that process should automatically be restarted. Easy development and easy deployment. It's very difficult for a development team to actually try and develop and test a batch job on their local machine. So providing an environment for them to actually develop your batch system is key. Also being able to make sure that you can minimize setup of that environment and boilerplate code and allow for easier deployment makes the development cycle of your batch architecture much easier. Higher efficiency, so being able to realize maximum utilization of your infrastructure resources running your batch job. And nobody likes to be called at 3 a.m. in the morning due to a failure, so keeping a automated workflow as much as possible so that you can minimize your operations profile. And above all, how do you make sure that you can ensure that, since you're running your batch job only for a certain period of time, you want it to be cost effective and not have to pay for infrastructure that you're not using most of the day. So what makes ECS compelling for running a batch processing workload? Well, firstly, ECS actually exposes a state management system via API calls. And you can utilize the state management system by calling it via ECS APIs to control and monitor your cluster, as well as understand state of your cluster. This particular state management system allows optimal placement from one container to tens and thousands of containers. And it also eliminates the need for you to run, procure, install, and manage your own cluster management software. ECS APIs provide performance at scale. So I believe a few months ago, we actually ran a test where we were continuously calling both list and describe ECS APIs continuously in a period of 72 hours against a cluster of varying size. And I believe at peak, we went above 1,000 instances. And you can see both the green and red lines represent P99 and P50 latencies. And ECS basically provided a near flat response. So ECS will scale irrespective of your cluster size. Flexible container placement. ECS has two inbuilt schedulers, one for running short-lived processes and one for running longer applications. And ECS utilizes both of these schedulers to optimally place containers on your ECS cluster. Since the state management system is actually provided or exposed to you via ECS APIs, you can actually utilize those APIs to build your custom scheduler as well if you have specific requirements for scheduling. ECS, again, is designed and integrated to work with many other AWS services. So you can launch your ECS cluster that would run all of your containers within a VPC, taking advantage of the VPC's network and security isolation features. You can utilize EBS, Elastic Block Store, for persistent storage. All traffic can be routed to your ECS cluster via an Elastic Load Balancer. And ECS integrates with IAM and CloudTrail for audit management and access capabilities, respectively. And so just like I mentioned, when you run your EC2 instances in a VPC, you can utilize security groups as well to control the traffic and access to your ECS cluster. And you can also use IAM access policies to make sure that you know who has access to your ECS cluster and what they can do with that cluster and your other ECS resources. So a few key fundamental components of ECS are tasks, containers, clusters, and container instances. So let's talk a little bit about what each of these mean. Firstly, tasks are essentially a grouping of related containers. And you can essentially run as many tasks on one instance as will fit. So what dictates how many tasks can run on an instance is the instance type that you choose. And a task essentially is an instantiation of something known as a task definition. But if we take a look at this example here, we have 4 separate containers that are part of the same task definition, an Nginx web server that's fronting a Rails application, which is supported by a MySQL backend and a log collector that collects log files from the Rails application. So when you instantiate a task definition, you're basically running a task on an ECS cluster. So what does a task definition look like? A task definition is a grouping of containers that you want running together. And you specify all these containers in one file. So if you can see, a task definition has a few separate sections to it, a family, a version, and you can utilize this to actually maintain task definition files, similarly to how you would maintain your source code via a version number, a particular name for your task definition. And essentially, a task definition, you can utilize it to model your application. So if you take a look at this particular format, you see that there's a container definition within the task definition. So when you specify all the containers that you want running together in your task definition, you need to specify exactly what those containers are and from which image should they be launched. So you specify the name of the container, the image, and any runtime variables that the task needs to be aware of when launching your container. So as an example of how this would look, in this case, the container definition tells you that the name of the container is a web server. It's from the Nginx image. All CPU, memory, and port mappings also are provided so that when this is launched by the ECS scheduler, it knows that it needs to look for a place on the ECS cluster that has the CPU and memory available. It links to the Rails application, and the essential flag is set to true. So what that means is if this particular container fails, the task will basically kill all other containers associated with the task definition. Clusters. So you want to be able to take all of your tasks, that define your containers together and run them on an ECS cluster. You can define an ECS cluster in 2 ways. It's a pool of resources to run your tasks, and it's also basically a grouping of something known as container instances. You can scale this cluster up and down depending upon the requirements that you have for your workload. And with container instances that form a cluster, an ECS cluster is essentially just an EC2 instance that is launched from an ECS optimized AMI. When you utilize the ECS optimized AMI, it comes with an ECS agent. The ECS agent essentially is what will talk to the state management system and registers your instance into an ECS cluster. Our ECS agent is actually open source, so it is available on our GitHub repo, so you can actually download it and install it on another instance type if you don't want to use the ECS optimized AMI. And your ECS cluster can actually contain EC2 instances of varying types. It does not have to be the same EC2 instance type. So just a few recommended design patterns, things that you want to consider when you're running your batch workload on ECS. So the first thing is being able to trigger your batch processes with Lambda. So what this provides you is the ability to use S3 as your definitive source of data input and data output. S3 is a supported event source by Lambda, so whenever data or a batch job gets inputted in your S3 bucket, it will trigger a Lambda function that can immediately start running a task on your ECS cluster with the data input from S3. And recently, Lambda actually released environment variables, so you can utilize those environment variables to tell Lambda that when this data gets inputted into S3, I want you to take this data and run it on this particular ECS cluster with, using this particular task definition. The next design pattern is creating a fleet of workers with ECS and SQS. So in this case, the ECS service your task definition, your container that's running in your task definition would call the SQS queue and receive the job. And what this does is this particular architecture pattern extends the capabilities of ECS to support event-driven ECS tasks, and also extends the capability of Lambda to provide the ability to run batch processes, workloads, or any type of workload that exceeds the Lambda time limit. So in this case, depending upon which event source that you want to use, whether it's a put to an S3 bucket, a put to a DynamoDB table, or a Kinesis stream, you can trigger a Lambda function that will take that data, input that data into an SQS queue, and automatically also start running a task that will go pull the batch job details from your SQS queue and start running it on your cluster. One of the last patterns I wanted to talk about was long-running batch jobs. So when you, I mentioned previously that Amazon provides two types of built-in scheduler, and one of those schedulers is for running long-running processes. So ECS allows you to run and maintain a specified number of instances of a task definition. And when you do that, when you specify that, you're essentially creating something known as an ECS service. So if any of those tasks should actually fail or stop, the service scheduler will automatically know that I need to maintain this many number of this task and this task definition, and it will automatically start one more task to make sure that it is keeping the number of desired tasks running at all times. And in this case, you want to be able to utilize spot instances. Since you're dealing with long-running processes, if you know that there's not a set time restriction, you can utilize spot instances or spot fleet to make sure that you can keep your costs down. Spot block also is useful for if you know the defined duration of what your workload is. Spot block provides a way for you to reserve spot instances for a certain period of time. In order for monitoring a cluster, an ECS cluster, and the ECS tasks running on that cluster for long-running processes, ECS recently released something known as ECS Event Stream for CloudWatch events, and this will send you near real-time notifications of the current state of your ECS cluster, as well as the current state of all the tasks running on your cluster. So just a few best practices to keep in mind. Store any type of persisted data and state in S3 or some other persisted storage. Try to minimize dependencies between task definitions. Try to keep as many dependencies as possible within the same task definition, so you're linking all of that together. Use spot instances and spot fleets to optimize cost. And then continuously monitor the state of your cluster using ECS APIs, since you have access to that. Utilize a shared pool of resources. There's a lot of debate around, how many clusters should I run? Should I run one cluster per app? Again, it's more or less a design decision that you make, but the more you're able to utilize, your infrastructure as much as possible by sharing pools of resources, the better utilization and cost profile you will be able to realize. And of course, take advantage of all of the services that ECS integrates with. Autoscaling, you can create an autoscaling ECS cluster so that it will scale automatically based on CloudWatch metrics. Launch your ECS cluster inside of a VPC. Control access to your cluster utilizing IAM, and then utilize scheduled reserved instances if you know that you need this much, the capacity of what your workload requires. So I want to introduce Will White, who's the engineering lead from Mapbox, and he's going to talk to you a little bit about how Mapbox runs batch on ECS. Thank you.
Thanks. Hey, everyone. Thank you. So I'm Will White. I'm on the platform team at Mapbox, and if you were in the previous keynote, this might be a little bit of a review about what Mapbox is, or you might have seen our CEO Eric on stage during the keynote with Werner this morning. Mapbox is about adding location to any application. We have customizable location services like maps that help you see the world in stunning detail. geocoding, which is our search that helps you find locations and addresses, and directions, which helps people get from point A to point B on time. We work with a lot of customers that are able to take our SDKs and drop them into their app, and together, all of our tools sort of come together, and the goal is to help change the way people move around the world. The Weather Channel is using us in their iOS and Android app to render animated radar and satellite maps, and they're also using our search to help people find the weather for specific locations really quickly. Airbnb is using us on the web, our JavaScript SDK, and they have a custom marker that shows the price for properties that are available to rent. And then someone like CNN, they're using us to help people understand where news is happening. They have a custom satellite-based map and a custom street map. And then National Geographic. They have an amazing city guides app that uses Mapbox to help guide users on amazing walking tours of the world's most iconic cities. Mapbox is powering over 55,000 apps, and our API reaches over 250 million users every month, unique users, and that number's growing. So in order to provide maps for all of these customers, we need to process a lot of data. So batch processing is a pretty critical element at Mapbox. We've really split our services into two groups. We have a batch processing group, and we have our API group. We're using ECS for both. But of course, today we're going to focus on the batch processing. I want to walk through two use cases. This is an image that comes from the MODIS satellite. We get one of these every day. And the biggest problem that you can see with an image like this is the cloud cover. It's an incredible resource, and the fact that it comes every day means that we have a lot of data, but we really want to find a way to get rid of those clouds. So the way we do this is basically doing a lot of pixel pushing. So we organize the various images that we get over the course of maybe several months to up to a year, and we sort them by brightness. So what this gives us is the darkest images are the most likely to not be covered by clouds. So we've really pushed all the cloud cover images to the bottom of the stack. Then what we do is we take the top of the stack, maybe the first 20%, and we average those pixels together. And if you do the math out on this, we're talking about trillions of pixels across that cover the world, and over 2 petabytes of data we have to process this way, the satellite imagery. That's because we have the entire world covered, and we have the entire world covered for every day of the year. The output is a gorgeous, cloudless, totally artificial map of the world that you've never seen a cloudless day like this in the UK. But we're able to use this technique to make a very, very crisp picture of the world, and it's really, really great for data visualization. Another use case that we use ECS for batch processing is building our traffic map. A lot of you have probably seen a traffic map like this. I don't know if you've ever wondered how it works. Well, the way it works at Mapbox is we collect billions of individual points from our users of our SDK, and we anonymize those, aggregate them, clean them up, and snap them to the road network. So it starts to look like this. So instead of those individual points, we now have, through a lot of processing, we've been able to snap them to the road network. There's another example. This data is covering entire cities. Here's where I'm based, Washington, D.C. We cover many cities and entire continents with this data. So it's a huge amount of data. In fact, it's 3 billion points every day, and that equates to about 100 million miles of worth of coverage that we're getting every day and processing into things like our traffic map. We also have other use cases for it, like detecting one-ways or turn restrictions, discovering entirely new parts of the road network when things change, or change in traffic patterns. It's incredibly useful data that helps us make a better map for our customers and really improves the quality of the transportation, helps people get around. So in both of these use cases, We noticed that as we went to build them, we noticed that we were seeing similar aspects of the patterns that we were following to execute. And obviously you're going to have EC2 instances. You're going to want to be able to scale that up, scale that down very quickly. We're always using an SQS queue. So to queue up our work, because we have data coming in, we want to create SQS messages for that, and then execute on those messages. And one of the biggest things that I think we overlooked at first, and I encourage you to pay close attention to, is error handling and reporting. Basically, what are your failure states, and how do you want to handle them? So that was one of the most important things for us to figure out. And those 3 points really encouraged us to build a sort of abstract some of the complexities around this and build a tool that we call watchbot. So today I want to introduce watchbot. This is an open source tool that we're releasing to everybody. It's at github.com/mapbox/ECS-watchbot. Watchbot is a library to help you run highly scalable AWS services that perform data processing. And here it says in response to external events. What that means is any message that you can put into an SQS queue, you can run watchbot on. So the way this works is you basically provide a container, it provides an SQS queue, you provide a container, a cluster, and that container contains, it describes what work you actually want to execute, and it will take care of the rest. So yeah, again, open source, I highly encourage everyone to check it out, github.com/mapbox/ECS-watchbot. Here's the basic architecture. Again, you have your SQS queue that's provided by watchbot. You have an ECS cluster that you also provide, and I can show an example of how to provide that in a second. And then ECS provides watchbot provides a watchbot container, a watcher container that polls the SQS queue and then runs the individual tasks for you for each message that it gets. One thing that we're doing is very often our ECS cluster is a spot fleet, and it's a spot fleet of diversified instance types. And that diversification helps us avoid interruptions in the spot market. So spot, you can bid on unused capacity on the EC2 market and get EC2s at a fraction of the normal price. But in order to use it at scale, you really need to diversify, because if the spot market demand goes way up on a particular instance type, you want to be able to move your application, distribute your application across the remaining available instance types. And that's really important. So the combination of spot fleet and ECS is kind of magnificent. So the cool thing about a watchbot task is you can do anything you want. Anything that runs in Docker, anything that runs inside a container, you can run in watchbot. You can use any language. It uses environment variables as its input. I'll go into exactly which ones are important in a second. And it uses standard bash exit codes as a success or failure indicator. You can control basically the retry pattern, success or failure, using exit codes. It's very intuitive, and it makes it a very easy interface. You can do any I/O you want, including using S3. That's the number one thing that we use. Source data on S3, pull it down on S3, do some processing, and then put the outputs back on S3, or in some cases DynamoDB as well. So looking at the environment variables, there's a subject, which is the subject of the SQS message, and then the message itself. And that's probably the most important thing to be aware of, is the message. There are a few other things here that are very useful. Sent timestamp, so you can react. You can say, oh, this message was created 12 days ago. You can take some sort of action based on how old the original timestamp is. Approximate receive count is another really useful one for some more advanced control on how jobs are processed. But the most important one is a message. The message can be any format you want, and as long as your task is ready to parse it. And JSON is, for us, JSON is the most popular one. In the demo I'm going to give later, we just use standard text, just straight up text. But JSON is a really nice way. You can sort of make a structured document. You can have properties that refer to files on S3 or documents in DynamoDB, inputs and outputs. So JSON, as long as your task is ready to do a JSON parse, then JSON is a really good choice for a message format. Exit codes, pretty straightforward. Again, 0, standard bash exit code, it means success. There are a few other exit codes that are sort of reserved for watchbot. Watchbot treats exit code 3 as a reject, and it will remove it from the queue and send a notification to an SNS topic. So you can hook that SNS topic up to PagerDuty or just have it email you directly if you don't want to share that burden. But this is a really good way to know when things are going wrong on your data processing, which is incredibly important. Again, monitoring is very important when you're doing massive amount of data processing, because the worst is when you wake up in the morning and you learn that you spent too much money doing data processing on something that has been failing all night. So monitoring for sure. Exit code 4 is a no-op, which means the message is going to be returned to the queue, and that's silent. And then any other exit code at all is an error. So if you want to use any other bash program inside that returns another exit code, it's going to be treated as an error. There's even more features, and they're all listed in the README. The documentation's incredible. It has features like logging, so it will automatically log, write its application logs to a CloudWatch log group. And those can be forwarded from the log group to other services like Splunk or Sumo Logic or any log aggregation service that you want for further analysis. You can send alarms to SNS, as I mentioned. This is really powerful. And it also has reduce mode, which is this is a newer feature. So you can process a couple thousand messages, and then you can give it a job. It will split that up into a couple thousand messages, distribute it horizontally across a fleet of EC2s, and then when all those, that's the map part, and when those jobs are done, it can run a reduce step, which will maybe combine all the output files into one, or maybe count up results of the output or summarize it in some way. So reduce mode is a really cool feature. Along with the reduce mode, it also is giving you progress tracking. So you can see 50% done, 60% done, all the way up to 100% done. So you can sort of see where you are in the task management. So that's a new feature. A big question I get a lot of times is how do you decide, why aren't you using Lambda for these kinds of things? In fact, we've been working on watchbot for a long time, and when Lambda first came out, we really were excited, and because we thought we could replace Lambda with a lot of things. But Lambda, we do make heavy use of Lambda. We use it for many, many, many use cases. We have hundreds, maybe even over 1,000 functions in our account. So we definitely use it wherever possible. But it does have some limitations that make it tough to use in every situation. Lambda, so watchbot gives us full control over the execution environment. So if you need to do something weird like change something at the OS level, override the C standard library, we do this. And you can do this in watchbot. You cannot do this in Lambda because you're sort of focused on the specific language that you pick when you configure your function. The biggest one, I think, is there's no limit on execution time. You can have your ECS job run as long as you want. We have jobs that, while I don't encourage it, they can run for hours or even days. In general, best practice is to keep your jobs small and short, because that means you can horizontally scale them easier. But that's not always possible. So watchbot gives you no limit on execution time. There's no memory limits, which is pretty amazing. So as long as you're fitting within the memory limit of the EC2 that's in the fleet that you're running, or the cluster you're running, then you'll be okay on memory limits. And with something like the X1, I don't think you'll be able to run out of memory too quickly. No concurrency limits. So Lambda, one of the biggest things is you might run into a concurrency limit or account-wide throttling on your account. So you have one Lambda function that's on bad behavior. It's using a lot of function calls, and that can actually disrupt other calls, prevent other calls from being made, because there's an account-wide throttling, account-wide invocation limit that can cause throttling. We've run into that a few times, and that's just not an issue with ECS. The one thing that I will flag, and this is a little confusing on the slide I'm realizing, is that watchbot doesn't support DynamoDB streams or Kinesis yet. That's coming soon. But Lambda is actually pretty good for this. So we do use Lambda. What we typically do, we'll have hook up a Lambda function to a DynamoDB stream or a Kinesis stream, and then fire a watchbot job into the queue. So one gotcha I want to flag real quick is that the ECS optimized AMI is EBS Boot. And one of the things we've run into is there are two things with EBS, reasons we don't actually use it. One is performance, and the other one is cost. So I'll start with the cost. When you get to running on the spot market and you're running EC2s at 90% what the normal price is, keep in mind that EBS volumes that come with an EBS Boot instance are charged at full price. There's no discount to an EBS Boot volume. So you might be saying, well, instead of 40 cents an hour for this instance, I'm paying 8 cents an hour. That's a really good deal. Let me spin up 1,000 of them, and this is what we've done. But then later, only to realize that our EBS bill is very high because we're just not used to running that many instances. So Spot unlocks the ability for you to afford to run thousands of instances. So just watch out for the EBS problem, where you still pay full price for EBS. And then the other thing we found is that it's just for the kind of data processing that we do, even with a lot of the amazing performance improvements that have been made over the last few years with EBS, we just can't get it to the performance, to get to the performance that we want, versus Instance Store, which is just there. It's just available. It comes with the instance for free. You get it with the price you pay on the spot market, and the results are pretty astonishing. So what we've done, just a heads up, that the ECS optimized AMIs are EBS Boot only, and we've rolled our own AMI that is Instance Store. So I want to do a quick demo. This is another open source tool. Well, it's sort of our open source implementation. It's called ECS Telephone, which is sort of a little bit of a toy implementation for using ECS. Also a public repo. In the process here, you're going to get to see a little bit about some of the tooling that we've built at Mapbox around using ECS and also just using AWS. I'm going to make this bigger. Okay. So the first thing I'm going to do is log into my AWS account. So we do everything through a tool called MBX for Mapbox. It's our Mapbox CLI. So all of the engineers at Mapbox are generally set up on this in the first couple days they work at Mapbox. And the way I log in is I have Authenticator on my phone. So I'm using two-factor authentication to log into my account. Everybody does two-factor authentication to get credentials. So this code, for the next 60 seconds, it's going to work. Then to log into the console, I just run MBX login. It's going to spit out a URL I can click on, and now I'm in my console. So I'm in a Git repo here. This is the ECS Telephone repo, and I can see what files are in here. There's a Docker file, there's an index.js, there's a package.json because this is a Node.js project. We can look at the code really quick. So this is a very, very simple example, a very simple script that basically takes the message. You can see the message is coming in here on this line through process.env, so it's an environment variable. And then that message is, we're picking a random word from the message, so I'm going to send a sentence to this task, and it's going to pick a random word from that sentence and replace it with another random word. It's sort of a silly project, but it's a good demo. So we're using the random words module from NPM to accomplish that. Then what we do with the sentence is we just feed it back into itself. So that's why it's called telephone. It's like playing a game of telephone with itself. So it's just going to perpetually feed more messages into itself. So in order to see what, I'm going to create a new stack. We create all stacks, all of our resources at Mapbox we create with CloudFormation. And we have a tool that we wrote to make this a little easier. I'm going to create a new one called Reinvent. So we sort of, actually I'm going to list the ones we have now. So I have one stack running called ECS telephone staging. I'm going to create a new one called Reinvent. So again, this is going to be using CloudFormation to do all the setup, and it's a really good way to keep track of your infrastructure. Infrastructure as code is being able to commit infrastructure changes to Git is incredible. So it's going to prompt me for the cluster ID. And a lot of people ask, how many clusters do you run at Mapbox? And the answer is we run 4 per region. We have a dedicated cluster for data processing. We have a staging and a dev version of that. And then we have a dedicated cluster for API services. And we have staging and dev for that. So we have 4 clusters, and then we have 4 clusters in every AWS region. So I know some people are setting up an ECS cluster, 1 per app or something like that. But as Asha mentioned, you might not be getting the most out of sharing resources if you do something like that. So try minimizing the number of clusters you're running. So I'm going to search for the ECS cluster that I want to deploy this to. ECS cluster processing staging. And I'm going to get the cluster ID. So just copy this as from the output of the CloudFormation stack and paste it in here. I'm ready to create the stack. I'm going to create the stack. So now going back to the console, let me make this bigger. So now we can see the crate is in process. Also got some nice output from Mapbox CLI. So Mapbox CLI, just a quick note, is wrapping a tool that we've open sourced as well called cfn-config, github.com/cfn-config. That's what's generating the output there. MBX is just wrapping around that. So if you're looking for a way to, a nice way, developer-friendly way to use CloudFormation from the CLI, check that out. It's a really good project. So we can see we're creating a topic. This is an SNS topic, creating a queue. We're creating IAM role so that our stack has permission to access certain resources. It needs to access things like S3 if you want to give it access to S3 or DynamoDB for getting inputs or delivering outputs. And now we're creating the service. Okay, and this is taking a little long. So I'm going to use the staging stack as a demo now, because this is taking a little bit of time. So the way you want to get to CloudWatch logs, so we're going to see the logs. So I'm going to SNS, and the way you actually push a message into watchbot is through its SNS topic. So I'll search here for telephone. I'm going to use staging, and here's the watchbot topic. And then I'm going to go to CloudWatch logs, and ECS telephone staging. Here we go. Oh, it's complete. Okay, so I'm going to publish a message to the topic. Here's the log group for the stack that I just created. There's nothing in it. Watchbot is running, so that's the only message that's there. But otherwise, it's ready to go. It's ready to receive work. And I'll give this a nice subject. I'll call it reinvent. And then the quick brown fox jumps over the lazy dog. So provide my sentence, and then I'm going to publish this message. So it's published. And now what we're going to start to see is watchbot's going to, again, for every time we get that message, going to pick a random word, replace that word with another random word, and then feed the message back into watchbot. So we got the message here. The quick brown fox jumps over the lazy dog. That's the first time we've seen it. I'm going to refresh again. Okay, not getting any other messages. While we wait for that. Looking at the code again. If you look at the code here, it's very easy to see how you can start to bring in other JavaScript libraries. You can start to make this a lot more sophisticated. So this is a very simple demo, but it goes a long way from here. This is where you can start to add in, and it doesn't have to be Node.js either. You can run on any language. Okay, I was expecting a lot more messages than this. Let me check the other one. Oops, this one broke. Well, there's nothing like a live demo. Sorry, everyone. That's all I had. Can we go back to the slides? Thanks. So yeah, quick demo gives you a sense of what you can do. Obviously, it's a little goofy, but you can really extend that to get a lot of power in your batch processing. So just to summarize some metrics from our deployment on ECS, we're running 14 data processing services in addition to our 21 API services. So that's 14 services that are dedicated to just doing data processing and batch. We've peaked at 3,500 container instances running in our cluster. So it's a pretty massive amount of computing, and that's distributed over a variety of different instance types. And we're on track this year to use over 500 million hours of compute, which is a pretty massive scale. That's all I had. Thanks. Please, I encourage you to fill out the evaluation for this session, and we'll hang out up here to take any questions you have. Happy to talk through ECS, Spotfleet, watchbot. And again, check out watchbot, ECS watchbot on GitHub. Thank you.